Well, here we are on our third installment from Chapter 14 on the Introduction to Inference. We're going to continue with the particular example we were doing in the last one. That is the last installment. That was where we had the sample of 100. We were given the population standard deviation of 5. And they wanted us to compute a 90, 95, and a 99% confidence interval. And we had a sample mean of 15. And these things were given to us, and we know the population is normal because our assumptions are met for this chapter. That we have a sample that we got by doing a simple random sample, that our population is normal, and that the population standard deviation is given to us. So we calculated the confidence intervals in the last time. We talked about the margin of error. That was the half width of our confidence interval, and we could even say what the length was. It's twice the margin of error. Or we could have just done a calculation on the range of our confidence interval. So as you can see in red, getting the range of that confidence interval, just taking 15.82 minus 14.18, we get 1.64. And that is exactly what the length of our interval is when we take 2 times the margin of error. So those are the same thing. So now we're going to change a couple of things around. The first thing we're going to do is look what happens if our sample size changes. So we're going to do a 90% confidence interval where our sample size is going to be 500, and then we're going to do one where our sample size is 25. So we have our first one where we had our sample size of 100, and then we have our second one with the sample size of 500. Let's take a look what happens when I calculate the confidence interval. I get a margin of error this time of 0.37. It's a bit smaller than the one above it when I had a sample size of 100. So the larger my sample size, the smaller my margin of error is, which in turn means that the width of my confidence interval also goes down. Because look at that, the length or width of the confidence interval for my sample of 100 was 1.644, and the interval length or the width of my confidence interval is 0.74 in my sample of 500. So if nothing else changes and we increase sample size, it seems like that the margin of error gets smaller, and so does the length of my interval. And we can see when we increase the sample size to 25, decrease it to 25, look how drastically longer the margin of error is. It goes from 0.37 from a sample size of 500 to 1.645 when our sample size goes down to 25. So again, what we see here is as our sample size increases, our margin of error decreases. So now I've got them in order, sample size of 25, 100, and 500. And we can see how the margin of error decreases as our sample size increases. So if we had to do a particular confidence level, if they wanted a more precise confidence interval, more precise means a smaller length, then we would have to increase our sample size. Now, let's see what would happen. Let's see what happens if everything stays the same, but our confidence level changes. So now let's take a look at what happens when we increase our confidence level. So we're going to take samples of size 25. All the conditions are the same. And so the 90% confidence interval, where n is 25, is 1336 to 1665. Our margin of error of 1.645. The overall length of my confidence interval is 3.29. Let's see what happens if we increase our confidence level to 95. Well, our margin of error goes up to 1.96. So the interval length increases to 3.92. Now let's look what happens if we go all the way to a 99% confidence interval. The margin of error increases to 2.575 and the interval length to 5.15. Quite an increase. So we see as we increase our confidence level, we increase the length of our interval. Now why is that? Well, let's think of the general formula for a confidence interval. So here we have the general equation for a confidence interval. Whatever the value for x bar is, will not increase or decrease the confidence interval length. That's just where we're going to start the confidence interval. So no matter what our x bar is, it's not going to do anything to the length of our interval. I hope you all see that, because we're adding and subtracting off a number from a singular point. So again, what's going to change the length is your margin of error. This is Z alpha over 2 times sigma over the square root of n. So remember, for the different confidence intervals, we have critical values. And so for the 90, it's 1.645, for the 95, 1.96, and 99, 2.575 is its critical value. So let's look at the formula. If we said that the margin of error is what changes the length, if I increase my confidence level, look at the critical values. What do? They increase. So it made sense that our confidence interval length will increase as our confidence level increases. But there's an inverse relationship with the sample size, because the sample size is in the denominator. And think about it. If you divide by a bigger number, the smaller my number. Think about a couple of problems. So just by looking at a simple example, if I have 100 divided by 50, I get 2. If I take 100 and divide it by a smaller number, let's say 25, I'm going to get 4, a larger number. So the larger the number I divide by, the smaller the number I'll get. So that makes sense that if everything else stays the same, if we increase the sample size, our confidence interval length will decrease. And remember what that means. So a more precise interval means that we have a smaller interval length, or that our margin of error is smaller. And sometimes we want a more precise interval. So 2 ways to do that would be to decrease the confidence level, would be one way to make our interval more precise, or to increase our sample size. And depending on what we can do, depends on how we're going to complete the problem. The NAEP quantitative scores, we want to find what's the average score for all young adult males. Please go on and read the problem. Now remember that we are to assume that the population is normal and that the samples we take are from a simple random sample. And this is the problem. We want to find, the mean score. So we have a sample of 840 men. Their mean quantitative score was 272. And we want to estimate that mean score, so we're going to do a confidence interval. And we're going to use a 95% confidence interval to estimate that mu for the population. Remember that our sigma was given to us as 60. So again, there's our standard error for our sampling distribution of a sample of size 840. So now this is a slide of just showing the underlying thing of a confidence interval. If we kept taking samples of size 840 and calculating their means, and we take each of those means and create confidence intervals about them, about 95% of them would include the true population mean. So this slide shows you, for the mean that we calculated, what the 95% confidence interval would be. It would be between 267.9 and 276.1. So again, looking at the underlying meaning, if we use the same procedure to estimate mu for many, many, many different random samples of size 840, they would lie within 4.1 of those means we would calculate, and about 95% of them would contain the true mean. And these are the different ways that we can do the interpretation written. You're going to have to know this for your mini-tabs, and also if you were to ever write anything up. We estimate that the mean NAEP quantitative score for all adult males is between 267.9 and 276.1 with a 95% confidence interval. Or you could write, we estimate that the mean NAEP quantitative score for all adult males is between 267.9 and 276.1 with a 95% confidence interval in parentheses. And this is a caution that I would like you to look at and read. It's very, very important. We don't want to say that, don't want people to think that we mean that 95% of all males will have scores between there. It's just statistical things. If we did this over and over and over again, our confidence intervals, about 95% of them would contain the true population mean. Thanks.